So we were discussing this morning a little bit how one of the sort of positive outcomes of the last year is how much easier it is to actually organize and attend talks, all over the world, have access to great speakers no matter where you are. There's no, having to fly people out and then put them up for like a day or two and then rearranging their entire week just to give a 45-minute talk. But we can also, now have all of that exchange from the comfort of our own offices, living rooms, kitchen tables, whatever it is we're sitting at to work. Okay. I think there's still a little bit of a stream coming in, but...
Hi, Florian. Nice to have you here.
Maybe I'll start introducing our speaker of today as more people are coming in. So welcome to the second edition of the DMI talk series this spring semester. Wonderful to see so many new and returning people, and I am extra delighted today to welcome Sebastian Ruder for a talk. Thank you very much, Sebastian, for agreeing. Sebastian, probably many of you who are familiar with NLP will know who Sebastian is. Even if you don't do NLP, you might have actually come across some of his work, as Sebastian is a prolific reader and writer who maintains a wonderful blog and updates on Twitter and various platforms on a wide range of topics in NLP and machine learning more general. Probably has done more to do community outreach to people than a lot of academic courses and seminars have done. Really, great resource for everybody who wants to get into the field or who is interested in specific topics. Sebastian is currently a research scientist at DeepMind in London. He semi-recently graduated, already a couple of years ago, while he was also working at Alien as a company. He has been prolific in writing not just the wonderful blog posts and explainers that I've talked before, but also a range of really well-cited great papers. And he's one of the few people whose PhD thesis you can, actually give to somebody and say, here, read this. This thesis will explain all your problems to you. So I'm very delighted to have you here, Sebastian. We're looking forward to your talk, and I'm extra happy that you chose to highlight a topic that's becoming more and more important in the NLP community, but also I think more generally as NLP and AI are becoming more ubiquitous. How do we make our tools work for everybody and not just those of us who speak English? So thank you very much, Sebastian, and the floor is yours.
Thanks very much for having me, everyone, and thanks so much, Dirk, for first of all the kind invitation and the very kind and very flattering introduction as well. Thanks a lot. And I'm gonna start sharing my screen now. Just a second. Cool. So I hope you can you all see that here?
Yep, loud and clear.
Okay. Very cool. Okay, yeah, so I think with okay, let me just change slightly the windows here that I can still so just grappling with the Zoom web application here. Okay. All right, yeah, I don't think I'll see you right now. I don't think I'll see the chat during the talk. So yeah, so if you have any questions, anything that is unclear, or you want to just more information about throughout the talk, you can ask directly or at the end as well.
Yeah, I was going to offer, I'll monitor the chat. So
okay,
if
cool.
you have a question, please just type your question in the chat, and then either I'll read it out loud if it's a direct question, or we can save it for the Q&A at the end.
Okay, sounds great.
So you don't have to keep the chat open.
Okay, awesome. All right, cool. So as Dirk already mentioned, the topic of my talk is really very much how you can use NLP not only for English, but kind of with the ideal goal of being able to apply natural language processing methods to most of the world's languages. In that context, I'm mainly going to be talking about methods that do transfer learning. And so talking about transfer learning, I think in general, it's kind of useful initially to get us on the same page and really talk about why it makes sense to do transfer learning in practice. And so I think broadly, transfer learning has been really useful for many different settings across the entire NLP landscape. And it's most useful if you transfer between different tasks that have some similarities, so that share some common knowledge about language. So whether they rely on similar representations or have some structural similarities. It's also very useful if the underlying tasks or languages share some common structure, which is the case for most of the world's languages as well. And in practice, transfer learning is kind of most practically useful if the labeled annotated data that we have available for one setting is particularly rare, which is the case for most of the world's languages, where really there's a scarcity and a lack of labeled and even unlabeled data.
Sorry, Sebastian. Just real quick. I think your mic is like rubbing on your zipper.
Oh, yes. Yeah, good point.
Is there a way to?
Let me. Okay.
I think that's better.
Okay, let me see. Yeah, thanks for the mention. All right.
All right.
Hopefully, like that's going to be better. Okay.
Okay, I think that should, because there was somebody in the chat mentioned the cracking, and I think that's it. All right.
Okay.
Sorry.
Yeah, and empirically, if you've been following the progress in recent years in NLP, you've also seen that transfer learning has led to most of the recent successes. And to just cherry pick and just highlight the progress on one particular standard task in natural language processing, which is named entity recognition. So the task of identifying whether an entity or a token or a phrase in text refers to a real world entity, or and to what particular kind of entity it refers, whether it's a person or an organization here. And this the standard dataset for this task, Cordell 2003, was introduced in 2003 here. And much of the early progress on this task was really due to learning better forms of representing words, whereas most of the recent progress in the latest years have been due to using deep neural networks combined with different forms of unsupervised pre-training. And both of these kind of methods or improvements can really be seen as different forms of transfer learning. And generally, overall, we've also seen kind of a similar trend over the history of doing cross-lingual transfer learning, in that firstly, the biggest improvements have been achieved using cross-lingual word representations. And most recently, over the last 2 years, many approaches have switched and moved to using deep contextual representations for learning multilingual representations. To give a bit of a broader context for transfer learning, I like to think, or I like to characterize the transfer learning landscape in NLP along 2 different dimensions. Whether the source and the target setting you're transferring between deal with the same or with different tasks. If we're dealing with the same task, then this has been typically studied as either domain adaptation, in which case the tasks deal with 2 different domains, or in our setting here, in which case we typically try to adapt between one task and where the data for that is available for training and the data where we want to ultimately evaluate on are in 2 different languages. And separately, 2 other useful strands of transfer learning are the setting where the tasks actually differ. So in multitask learning, we have data in multiple tasks available, and we generally try to train a joint model on all of this data. Whereas in what I refer to here as sequential transfer learning, we have one task that where we have usually a lot of data on. We want to learn useful general purpose representations, and then we want to apply these representations to a downstream task of interest. And this is a setting that has led to most of these recent state-of-the-art methods like BERT, and to a lot of empirical successes in NLP. Having said that, the kind of bigger issue at the heart of this talk is the issue of language diversity in NLP. research in general. And with that, I mean the kind of the contrast between the number of languages spoken around the world and the few number of languages, predominantly English, in which NLP is typically applied to. And in practice, I think this leads to two big practical implications. The first one being that by just focusing on English and a small set of other high-resource languages, NLP research and NLP and language technology applications in turn are really systematically excluding the more than 3 billion speakers of lesser resourced and minority languages around the world. And to just give one out of a plethora of possible examples that would be experienced by these minority language speakers in their day-to-day life. If you imagine in a post-COVID, post-lockdown world where you can actually go out for dinner and you're in a place like New York and you use a popular maps application to enter a query, you're provided with a set of different restaurants. If you enter a similar query in another language with a lot of resources like Spanish, you're provided with a similar set of options. But if you enter the same query in a language with much less data, such as Basque, you're provided with no options at all. And given that this is an issue for what is still a European language, Basque, and data that is very easy to obtain and very commonplace, like data about restaurants, you can imagine how big of an issue this is for most of those other languages and for data that is much more critical, such as data about clinics or healthcare. And the second issue for NLP research in particular is that as a community, by just focusing on studying this one particular setting, English, we might be overfitting our methods and the inductive biases that we encode our methods to properties that hold for English, but might not generalize that well to other languages. So while we've seen a lot of progress recently on NER, question answering, and a lot of other tasks in NLP, most of this progress really has been only demonstrated for English and a small set of other languages with a lot of data. And so the general solution or the general paradigm, I think, that can help us bridge to some extent this gap relies on learning cross-lingual representations. And if you've practiced NLP or computational linguistics before the deep learning era, the standard approach pre-deep learning to learn language-specific models or to learn language or models for other languages is typically to create features and specific annotations for each particular language and to train separate models on each of those languages. Whereas now, using vector representations and deep neural networks in particular, we have methods in our hand where we can construct a common representation space that can be shared between all of those different languages and that can jointly represent meaning not only in one, but in multiple languages at the same time. And this then leads us to hopefully be able to transfer whatever knowledge we've learned in one language to other languages as well that we care about. And so this, for context, the transfer learning formula that has been very useful so far in English and monolingual transfer learning essentially looks like this. Given a large collection of unlabeled documents, you can apply your representation learning method of choice to those document collection, like Word2Vec if you care about learning word representations, or BERT if you want to learn a deep contextual model. And then, provided you have some amount of labels in your target task, you can use those labels to fine-tune your model on the particular task of interest. Now, for cross-lingual transfer learning, the setting is very similar to this monolingual setting, with the main difference now that in the pre-training step, instead of learning just representations for one language, we try to learn representations that put words and phrases that have similar meanings in all of those languages close together in the same embedding space. In the second step, we then typically fine-tune our model on data of a language where we have a lot of data in, such as English, often for convenience. And then, given that our model has learned representations that are generalizable or that can transfer across different languages, we can then simply fine-tune, or we can zero-shot transfer those representations to the new language by just providing the fine-tuned model data of the same task it has been trained on in English data in the new language. And here you can see, for instance, the task of natural language inference, where model needs to assign a relation between a premise and a hypothesis, whether it is an entailment or a contradiction or just simply a neutral relation. And we can do the same task in English and in Spanish, even though we've only seen label data in English for that particular task. Now, as I mentioned, these representations can be learned on different levels of meaning. Initially, most work is focused on learning these representations on the word level, but most recent research has very much looked at sentence level and deeper representations, which is also going to be what I'm mainly going to be focusing on throughout the remainder of the talk. However, as I still think that most of the work that we're currently doing really takes inspiration and builds on all of the work that has been going on previously in terms of learning word level representations. If you want to learn more about those, I've co-written a survey and an ACL tutorial in 2019 that I think are good resources for learning more about these word level representations. Now, for the rest of the talk, I'm going to be talking about three main aspects. Firstly, I'm going to give you a bit more detail on how exactly these the current state-of-the-art methods for multilingual modeling and cross-lingual transfer learning actually look like. Then I'm going to talk about practical methods that you can use yourself for adapting these models to languages with a lot fewer data. And finally, I'm going to talk a bit more generally about high-level trends for evaluating these methods and limitations and deficiencies of the current generation of these models. So starting with the first part of the talk, to get us all on the same page, if you're not familiar with kind of the recent generation of models in NLP, most or a very strong baseline method in current NLP transfer learning is the so-called BERT model, which is a model that consists of a stack of transformer layers that is pre-trained on a large number of unlabeled documents, often Wikipedia or documents from the web, using the task of masked language modeling, where a random fraction, typically around 15% of the tokens in the input, are masked. So they are assigned this mask token, and the corresponding mask words are then predicted in the output. And both this model architecture combined with this pre-training task has been shown to demonstrate state-of-the-art results across a wide range of different NLP tasks, and has really been shown to learn very generalizable and general purpose representations about natural language. And the main kind of important thing, or the main important aspect here, is that the model itself consists of multiple stacks of transformer layers, which I'm going to talk a bit later about in depth, and that it does this sort of masked language modeling. The model, as I mentioned before, in general, in this transfer learning setting, is then simply fine-tuned on data of a task of interest, again, such as natural language inference here, and then can be directly evaluated on that task. Now, many models that have been very successful in monolingual transfer learning have also multilingual equivalents. And one of the strongest baseline methods for if you want to do multilingual learning these days is a multilingual analog of monolingual BERT, known kind of naturally as multilingual BERT. And this method is very similar to the monolingual BERT that you just saw before, with kind of the key difference being that now the vocabulary of this model, so BERT itself also has a BP vocabulary, so it doesn't have single words or tokens in its vocabulary, but typically so-called subwords, which are basically words split into smaller chunks based on frequency. And in this case, because multilingual BERT is now trained not only on data of English, but on data of multiple languages, the vocabulary also covers many different languages. And one side effect of that is that now words that have the same spelling in different languages, so that have the same string, are also associated with the same embedding. Now then, if you have this BERT architecture, again, as before, you can now train multilingual BERT if you have the available compute the same way as you did in the monolingual case, using masked language modeling, now not only on English, but on data on many different languages. And as we've seen before, this model can be used by fine-tuning it on data of a target task in a high-resource language such as English. So here, again, in natural language inference. And then it's typically evaluated by So you should transferring it to data of the same task in a different language. Now, one big problem or one kind of very crucial trade-off of these state-of-the-art methods is what has been known or referred to as the curse of multilinguality, which essentially refers to the trade-off between the amount of parameters in your model and how many languages you can cover in the pre-trained data and in the parameter space of your model. And as you can imagine, if you've done any sort of multitask learning over different tasks with models of different sizes, the more parameters that you have available for each particular setting, the better generally the performance is for your model. And the same thing we can observe also in the multilingual setting, where you can see here on the right the performance on this cross-lingual natural language inference tasks as you scale up progressively the number of languages. And we have the performance broken down here for languages with little label data or little data in the pre-trained data. So low-risk languages here, high-risk languages with a lot of data in pre-training, such as English, German, Arabic, a lot of Indo-European languages, and just the global average here. And what we can see here is that if you increase the number of languages, there's a small bump in terms of low resource performance due to positive transfer from just having a few more similar high resource languages where the model can transfer performance from. But then generally the performance deteriorates as we have more languages, with the model generally performing the lowest on average if it is trained on the largest number of languages. However, if you add more capacity to your model, so if you make sure that for each setting the model has more capacity to allocate, performance can be improved across all of those different settings. And current state-of-the-art methods such as multilingual BERT and XLMR, which is simply a larger version of multilingual BERT, try to strike a balance by having between 200 million and 550 million parameters, while covering about 100 languages in their pre-trained data.
Sebastian, there was a question whether the words from each language are pre-embedded on pre-trained vectors or whether they're fed as one hot encoded vocabulary.
Sure, yeah, so all of the vocabulary, so generally the vocabulary of these methods is really is trained or is kind of generated once using this BPE algorithm. So you apply that, so given your unlabeled data in many different languages, you apply this BPE algorithm to the data, and it then gives you the corresponding kind of way of splitting each word and the corresponding subwords in those different languages. So yeah, generally these, so this is the vocabulary of these methods, which is generated from scratch. And then the embeddings for the vocabulary are trained jointly with the rest of the model on this huge pre-trained data. People have looked for using, so in practice, like one kind of very big downside of these methods is because they require lots of data in different languages, and it's very expensive. So in practice, these methods have really only been pre-trained by very large institutions or corporations like Google or Facebook. But if you wanted to apply them yourself or to pre-train them more efficiently, I think using pre-trained representations or pre-trained word embeddings can be quite useful as well. Cool. So so overall, I think on the surface here, these multilingual models already provide a lot of benefits in that they can give you somewhat reasonable performance for a large number of different languages. However, in practice, in order to actually be able to use them properly for practical applications, we would really like to be able to bridge this gap, not only between high-risk and low-risk languages, but really try to improve performance for each of the different languages in these large multilingual models. And that applies to both languages that were seen in pre-training, so languages that are in those 100 languages seen by the model, and languages that the model has not even been pre-trained on. And for doing well in those languages, I'm gonna talk about a couple of different methods that are in practice quite efficient and easy to use, and also I think useful for different other settings where you would like to adapt your models to. And the main methodology that I'm talking about here is called adapters or residual adapters. And these are essentially very simply bottleneck layers consisting of a feed-forward down and a feed-forward up projection that are inserted between an existing model's layers. And to make that a bit more concrete here, we can see, so previously I kind of showed you the transformer model here. And here it is one of those layers just broken up in a bit more detail. So each of those particular transformer layers, transformer blocks, consist of a multi-head attention, some addition and layer normalization, as well as a feed-forward protection and another layer normalization layer. So this is kind of the standard way these layers are structured these days. Okay. And now for using a adapter with this method here, the adapter is simply inserted into a position in this existing layer. We found that inserting it between the different layer normalizations works quite well in practice. And as I mentioned, this adapter layer is simply a feed-forward down projection, a feed-forward up projection, coupled with a residual projection from the input. And what these adapters allow us to do in practice is to allocate a small number of additional parameters, so some additional capacity for the particular languages that we care about. So instead of really having to surrender to this curse of multilinguality, and that really forces us in having very few capacity available for languages where we don't have a lot of pre-trained data in, we can use adapters to selectively allocate more capacity for these low-resource languages. And adapters, and we can do this. So the main reason why this works is because adapter layers are kind of encapsulated and treated separate from the remaining parameters of the model. So while adapter layers are trained, all of the other parameters of the model are fixed. And in practice, these adapter parameters are learned. So you can imagine them being learned as capturing transformations that make the underlying model more suitable to the particular setting you're learning these adapters for. So in our setting here, for instance, we are using masked language modeling, the pre-trained task that I mentioned initially, to learn language-specific adapter parameters on data of the particular language, such as English, or a language with much fewer data in practice, such as Quechua. And these adapter layers, because the remaining parameters of the model are fixed, essentially then try to capture transformations or capture knowledge in them that, without changing any of the other remaining parameters of the model, still make the underlying model more useful to the particular language. So in general, because we fix these underlying parameters also, the very nice thing is that adapter parameters are interchangeable. So we can learn these adapter parameters separately, see for English or Quechua here, and then in a downstream setting, we can replace the English parameters with the target language we actually care about. And the other component here that I haven't mentioned so far is what to do about the underlying vocabulary. So far, I've just mentioned adapter layers that can be used to modify the parameters of the transformer layers and of the deep layer layers of the model, but also for dealing with a new language, you might want to allocate additional capacity as well for modeling changes that are on the embedding or on the token level. And for doing that, we can similarly as well use adapter layers on the token level. However, there's kind of one caveat here, in that in these state-of-the-art methods, the input and output embeddings are typically tight. So they have the same parameters, with the output embedding layer simply being transpose of the input embedding layer. So in order to take that into account and not have to learn a separate adapter at the output embedding layer that we would end up discarding anyway, we can instead constrain the adapters to be invertible, which allows us to use the same adapter layer that we learned for modifying the input token embeddings, also for modifying the output embeddings at the output embedding layer during masked language modeling. And in practice, for downstream settings, if we don't do mask language modeling, we only need to use the adapter layers on the input embedding layer anyway. So the entire kind of framework that we are proposing here uses adapters in a couple of different settings. In the first step, if you want to adapt your model to a data in a new language, you can learn what we call here language adapters for both your source language, so the language where you have label data in for your task, as well as your target language, the language you want to apply your model in. Using this pre-training task mask language modeling on data in both of those languages. Here we use data in Wikipedia. And as a result of this step, we have these language adapters that capture in them some language-specific knowledge about transformations that are relevant for that particular language. In the second step now, we also want to learn, we also need to learn something about the target task, but in this case, for the adapters to still be useful, we can't fine-tune the entire model, because otherwise the parameters would change too much from the setting to which the adapters have been trained for. So instead, we also learn an adapter that is trained particularly on the source language for the particular task. So in this case here, we stack this task adapter on top of the source language adapter and hope that because the source language adapter already learned language-specific information about English here, that the task language adapter can just focus on capturing language-agnostic information that is just relevant to the particular task, but hopefully generalizable across different languages. And in the target setting now, similarly to the zero transfer setting to before, we can now apply this method to data of the same task in different language. Now, simply by replacing the source language adapter, which captured relations for the source language, with our target language adapter that has learned target-specific representations, and applying it to data in the target language. And just to kind of highlight and emphasize here, kind of the, I think, very useful aspect of this particular setup in practice is that we can completely decouple the expensive pre-training and fine-tuning steps. So we can really fine-tune we can learn these adapter representations completely in isolation from each other. And then use them interchangeably for different target languages and different target tasks that we care about. While only having to learn these adapters once for each particular language. Now to just show you some results as well for this method, we evaluate on 3 different tasks. I'm mainly going to be showing results for named entity recognition here. And here in this setting, we evaluate on multiple transfer directions. So we transfer from a source language on the left here to a target language on the bottom. And in every setting, the languages are sorted based on the amount of pre-trained data available, and the 6 languages to the right here are furthermore languages that are entirely unseen by the model during pre-training. So languages where the model itself, this XMR model, which we use as a foundation here, has not been exposed to during pre-training. And what we can see here is the model particularly excels at transferring from this block of high-risk languages to languages with very little data or that have been unseen during pre-training. So here the performance is shown in relative improvement over this XMR baseline, and we can generally see here that for the green values, in some cases, this method is able to improve over this applying XMR by about 20 or even more F1 points. However, separately, we can also see quite reassuringly that even if we transfer between very high-risk settings, we still get very competitive performance by just applying the baseline method to this setting as well. The other thing that I mentioned before, because adapters are kind of very contained and only and just need to be trained once. We've also worked on a framework to make them more easily accessible and basically just plug and play, which is called Adapter Hub. So here, if you're interested in like doing multilingual NLP or even doing domain adaptation or working with representations for different low-risk settings, there are already a number of adapter layers available that you can simply download and use in your application of interest. Cool. All right. So from the settings, so previously I kind of mentioned the two settings of dealing with languages that were seen by the model and languages that were unseen by the model during pre-training, which is arguably a harder setting to adapt to. However, there's even kind of a higher degree of difficulty, which is dealing with scripts, so languages where the entire script, so the entire vocabulary has not even been seen by the model. And just to give you a couple of examples here, you can see here tokens or symbols in 3 different languages that are not available or that are not part of the pre-trained data of multilingual BERT. And yeah, to me personally, like all of these languages, I hadn't seen them before. So I'm curious if anyone recognizes maybe one of these languages. Yeah, you can write in the comments or in the chat if you want. If not, these languages are from kind of 3 different regions in the world. We have Amharic, an Ethiopian language, Tibetan, and Divehi, an Indian language, particularly spoken in the Maldives. And what I think is quite stark or quite challenging about, like, if you think about this setting, is if like for in this setting where you try to deal with entirely unseen tokens, you can imagine how text in these languages looks to a multilingual model that hasn't been exposed to any data of such languages. So if you try to feed in data in those languages to multilingual BERT, this is what multilingual BERT would see. So tokens in those languages would simply be represented and associated with the unknown token, and multilingual BERT, just applied in the standard pre-training fine-tuning setting, would not be able to learn any meaning or do anything useful for these languages with unseen scripts.
Sebastian?
Yeah.
Sorry, there was a question still on the previous like heat map, basically. Do you have an idea why there are some negative transfer on some pairs? And it seems that Arabic seems to be very good source language. Do you have any idea why?
Yeah, that's it's really great question. I think in practice, I mean, some as we can see here, like a few. I think particularly for some of the transfer from some of the low-risk languages, I think because the some of the NER data that we're using here, which is based on kind of weak supervision from Wikipedia, is somewhat noisy, and some of the low-resource data sets in particular are quite small. So I would expect some of these negative trends here for the training or for the user source language being simply due to kind of variation in the training data, or maybe that in those cases the task adapters could not be learned as effectively. Whereas for Arabic here in particular, I think that, yeah, I guess in that setting, yeah, I would kind of think that Arabic is comparatively like a bit, even though it has a lot of data available, the fact that it uses a different script for compared to most of the Latin languages seen during pre-training, that it's not that well represented in kind of this XLMR baseline model that we're using, and that's why we're getting kind of a big boost by learning these dedicated language representations for Arabic. Because we can simply allocate more capacity to them.
Mm-hmm. And there was a follow-up question about the adapters. Most of them seem to be feed-forward neural networks. Mm-hmm. Do you have any experience what depth is appropriate for those feed-forward networks, and whether have you experimented with different architectures?
Yeah.
And if so, do you have any experience with what that means for performance?
Sure, yeah. So generally, these adapters, so the adapters I mentioned here are just one layer of feed-forward network. So really parameterized like as simply as you can imagine. I think people have tried as well using deeper networks, but generally there's really this trade-off with the adapters of trying to use as little capacity as possible to make them kind of as scalable as possible, because in practice you want to use very few parameters to be able to learn kind of a lot of new adapters for your different settings. So that's generally the trade-off here. And in practice, we found that I think we use one particular kind of size for this hidden space or the bottleneck in the adapter layer that yielded quite a good trade-off in that in the end, the adapters make up around 1% or 0.5% of the entire parameter space of the model. So it's a very negligible impact compared to the benefit you get from them. Right, cool. So I hope with this example, I could kind of demonstrate that in order to deal with these unseen scripts, we really need fundamentally different methods, and we can't, and simply the method that we just proposed earlier of adapting or learning some transformation based on the vocabulary or of the hidden layers is not simply, or it's not directly applicable in this setting. And this based on also recent work with people from University of Darmstadt and Cambridge. And in this setting, we've studied, there's been a few recent work that also looked at a similar setting of adapting not to unseen scripts, but at least to other languages. And one very strong baseline and one very simple baseline as well that you can use in this setting is to simply learn a new vocabulary for your new language. So for the data often from Wikipedia, you can simply train a new tokenizer on that language. And then you can freeze the remaining parameters of your model here and only learn new token level representations for that particular language while keeping all of the other parameters fixed. And this has been an approach that we proposed last year at ACL, and as well some other people proposed variants of that. And what we showed last year is that even though even in this case, the remaining parameters of the model don't actually capture any like new information for the target language. As long as you learn this token level representations, the model is still able to figure out an alignment with the remaining representations of the model. And what we can see here in the following, and what other people have shown as well, is that if the underlying model is multilingual, so if you already capture some underlying information across different languages, then it's easier to learn these new token level representations even for a new language. And in our setting here, so you can do that basically just with a standard multilingual BERT model, freeze the model and just learn these new token level representations, and then doing zero transfer. The only difference is that instead of when you apply the model to your target language, instead of using the token level embeddings from your source language, you simply substitute in those new token level embeddings from the target language. In our setting, we're doing effectively the same thing as we did with MADX. So we freeze the entire parameters and we learn now not only the language adapters, but also these new token level representations for the target language. Now, as you can imagine, by just doing this token level representation, the model, if it might be able to figure out some alignment with the remaining parameters of the model, but the alignment itself is might be very inefficient, or the model might not actually be able to use any other existing information that is already contained in this multilingual model. So one additionally simple way in which you can make the task for the model easier of learning these target language embeddings in a new language is to use what we call here lexical overlap initialization. So for many languages, even for languages where most of the symbols haven't even been seen by the model, there will still be a number of tokens or symbols that occur in the training data of the multilingual model. So often this can be simple things like numbers, punctuation, or it can be names of cities or states, such as New York. And those names, and telling the model that it's likely the representation that it should learn for those new tokens should likely be similar to the representation of the existing method by using the pre-trained representation as initialization can provide the model with useful information for learning better alignment. So in this case, we do the same thing as just in the baseline method that I just mentioned, but with the additional step in that we initialize tokens that already occur in our existing vocabulary with their pre-trained representations, and then we just pre-train them again using masked language modeling now on data of our target language. Now, these are two baselines that are very strong in the setting, but both of them don't really go beyond using any more than the surface level information in terms of a lexical similarity of how similar the spelling or how similar different words are. So in addition, we try to propose, we're proposing here an additional method that also allows us to incorporate some of the potentially additional information that might be captured in the embedding matrix of the model. And in particular, here we propose to factorize this initial pre-trained embedding matrix X, where V here is the dimension, the size of the vocabulary, and D is the dimension of these embeddings, often 768, into lower dimensional representations. So these are simply F. So again, same size as the vocabulary with just smaller number of representations, and using different up projections. And these up projections essentially can allow us to factorize and code general properties of the source language embedding matrix into either one or multiple different abstractions that might be able to kind of account for different language families or different languages with different characteristics. Whereas here, these low-dimensional representations capture simply low-dimensional representations of the input tokens. And the main kind of additional here, the main thing that we need to make this work in practice is for the model to learn an assignment. So because we can use multiple abstraction matrices here, we also need something that tells our model which token should be associated with each particular abstraction. In which case we define here an assignment matrix I that consists of basically concatenation of column vectors, where in each column vector corresponds to one particular abstraction, and each cell is either 1 if the token is associated with that particular abstraction, or 0 if it's associated with one of the other ones. And in practice, we kind of diagonalize these column vectors here. So we essentially end up with something similar to an identity matrix, because in the setting where we only use one projection, in this case, the column vector here just amounts to an identity matrix. So what we have in the setting where we just use one projection is kind of just a standard formulation of semi-non-negative matrix factorization, which can be used with existing algorithms. And in the setting with multiple algorithms here, we can kind of use more sophisticated methods like k-means or using a neural network for learning these. And for target language now, kind of the main difference here that for target language, we don't now learn new pre-trained embedding matrix X, but just a smaller low-dimensional representation F prime here. And yeah, a few more details. I'm not going to go into more details here. You can go to the paper if you want to read more about that. But in the interest of time, I'm just going to cut that a bit shorter, and we can talk about kind of more details in the questions afterwards. Just going to briefly mention some initial results from that method here. The setting is similar to what we had before, pre-training on Wikipedia and evaluation on named entity recognition. Here, in addition, we compare to transfer from different high research languages to languages seen during pre-training, languages that are unseen but where we've seen the scripts, and languages with entirely new scripts. And we look at a number of different methods here, in particular multilingual BERT, which I mentioned initially, MADX, slightly improved version of that method, where we don't have an adapter in the last layer, which we found to work better empirically. The kind of initial baseline method that I mentioned of just learning new embeddings that are randomly initialized and learning these embeddings with a lexical overlap initialization, and as well one variant of our method where we learn these 10 different abstractions with k-means for the initial assignment, and then also using lexical overlap initialization to initialize these low-dimensional representations for the target language. And what we can see here is that if so this is basically averages across all the different source and all the different target languages. We can see here that in the standard setting, just learning embeddings here with the lexical overlap initialization, really, even for languages that have been seen, so they've been covered during pre-training, works exceptionally well. So it really is able to outperform multilingual BERT and even our previously proposed approach by quite a large margin. at the expense of having to add quite a large number of additional parameters for each particular language. And in contrast, our method is slightly worse, but a lot more parameter efficient. Now for the setting where we have to deal with unseen languages, but seen scripts, we can see that our method slightly outperforms MEDX here, as well as the embedding learning approach with lexical initialization. And generally, if we average over all different settings, then our method performs the best. And finally, if we look at entirely new scripts, we can see here really kind of the problem that I outlined initially with these methods, in that multilingual BERT and even MEDX perform substantially poorly. However, if we learn these dedicated target language embeddings, we can really get quite a substantial boost in performance. And what was quite surprising to me personally is that by using this lexical overlap initialization, we even see a substantial boost for languages where most of the symbols don't occur in the pre-trained vocabulary. So lastly, I just want to kind of show you or give you a brief intuition, basically, for even those unseen languages, what these lexically overlapping tokens actually look like. And in particular, I'm just showing here for Tibetan, Khmer, Divehi, which are all languages where the script has not been covered by the pre-trained data in multilingual BERT. And we can see here that some of the tokens here are actually numbers. A small subset of tokens are also simply Latin characters, simply A, B, or C or so. But with the largest subset of characters just being simple characters, being symbols in probably other scripts that are not that are seen by the model during pre-training, and where this lexical overlap initialization helps particularly. And if we look simply at the longest lexically overlapping subwords, we can see here that most of them are English in Latin script, and yeah, most of them kind of referring to like general concepts, and some of them might even kind of hint, for instance, for Tibetan at possible use cases or possible ways in which English language or other language text might be referred to or perceived in that particular language. All right, so I'm almost, I think, out of time here. I'm just gonna try to make the last part relatively brief. And in this case, I'm just kind of briefly talking about a kind of more large-scale evaluation and benchmark that we proposed for evaluating these multilingual representation methods on a diverse set of different NLP tasks in different languages. And in particular, we kind of chose a number of different tasks that kind of among them require different forms and different capabilities in terms of natural language processing for performing well in them. And you can see them roughly ordered here in terms of the complexity of natural language understanding that might be required to solve them. And after evaluating a model or a multilingual model on these different scores, similarly to monolingual equivalents such as GLUE, we're also provided here with a combined score that can serve and give us a glimpse into model's cross-lingual generalization ability. For selecting these tasks, we've tried to strike a balance between different criteria. In particular, we want these tasks to be difficult, but still diverse enough. We also want them to be efficient enough to use, so that even as practitioners with not a lot of compute available, you can still, or those people can still evaluate them. The task should be inherently multilingual as well as accessible to use. For choosing the languages, we try to strike a balance between having enough unlabeled data available to learn useful high-quality representations, as well as maximizing the diversity of languages that we chose. And the resulting benchmark covers around 40 languages from 14 different language families. For the evaluation scenarios, essentially what I mentioned already before, given a pre-trained model, we fine-tune that on data of a task here in English and adapt that via zero-to transfer to data of the same task in different languages. And in practice, because we typically have evaluation data in many languages available, this setting allows us to do this evaluation very efficiently because we only need to fine-tune the model once and can evaluate them directly on all the data of all target languages. We evaluate a number of different methods here, which I mostly mentioned before, as well as a couple of other standard baselines using translation multitask learning. But I'm just going to briefly mention the results for XLMR here. And in particular, I'm kind of taking a high-level snapshot of the average performance across different tasks, across different language families here, which you can see here, where each particular data point represents the performance on a particular language associated with that respective language family. And we can see overall that model performance on some of the easier tasks on the right is close to human performance in English. However, on the more challenging question answering tasks, model performance, even in English, is still further away from this red star of human performance. We can also generally see across the board that there's a substantial gap between performance in English and performance on these other languages, and that scores for these simpler sense clarification tasks are concentrated in relatively small range, whereas we see much wider spread for scores on these other languages. And generally, particularly for tasks that require us to transfer structural or syntactic information, in the zero-shot setting, we found them particularly challenging for these methods. So particularly for MER and part of speech tagging, we found these methods to struggle quite a bit with transferring to languages that are structurally dissimilar. Yeah, we can see a similar trend as you might expect when averaging and breaking down performance across different language families, in that we see the highest performance on languages that are represented a lot in the pre-trained data, like Indo-European languages, and much lower performance on other language families. So to sum things up, overall, these current state-of-the-art methods still fare comparatively poorly on these more distant languages and languages with limited training data. And we also made a leaderboard available where a number of different approaches have been submitted. And since the initial analysis that we did for this paper, there's been kind of stark improvement in terms of average performance on this leaderboard, with the largest improvement having been achieved on retrieval tasks. So tasks where you, given a sentence in your source language, you have to achieve the corresponding translation in the target language. However, most of these different methods have, most of the improvements on this retrieval task have not been achieved by more powerful encoders or more innovative pre-training strategies, but simply using additional data, mainly using translations for additional fine-tuning. So lastly, if you're interested in terms of evaluating on this benchmark, we've made code available in the Transformers library, as well as scripts where you can easily download and fine-tune data and fine-tune models on them. And we additionally made available automatic translations where you can analyze your methods as well in terms of performance on some of these other tasks. So in conclusion, I hope I was able to highlight that adapters itself are quite a powerful paradigm in terms of alleviating this curse of multilinguality and allocating additional capacity for different target languages. That particularly for dealing with unseen languages and new scripts, simply learning new embeddings with lexical overlap initialization is very powerful. That cross-lingual transfer itself still has many challenges, and particularly generalizing to low-resistance languages, and for structural or syntactic tasks, it's quite challenging. And finally, I demonstrate Extreme as a benchmark or as a means to get a window into models cross-lingual generalization ability. And if you want to read more, here are the papers that I mentioned throughout the talk. And yeah, I want to thank you all for your attention, and this work would not have been possible with all of these collaborators.
All right, thank you very much, Sebastian. So we had some questions throughout, but we also have a little bit of time for questions now. So if there's anything that came up during the talk, something you'd want to know, this would be exactly the time. I see there's one question in the chat, but I guess at this point we can also open it up. So Jan, do you just want to unmute and ask your question directly? Questions?
I don't know if you can hear me.
Yeah.
Okay, yeah, it's about the subwords and the choice of subwords for these multilingual tasks, because it seems that performance could depend on where you break up the words of the different languages, especially if you have languages that are rich in compounds or morphology, where I presume it could make a difference. So do you have any experience on that? And the second language related to this a little bit is whether if you have different scripts, as a different script for a different language, would transliteration use with that, be any use with that?
Yeah, those are two great points and two great questions. So regarding the first question, the role of subwords. So in practice, we've noticed that they do in fact make a big difference. One issue as well as here, simply kind of the data, these tokenizers. Well, I think we can kind of disentangle that into a couple of different problems. The first one being BP. So this frequency-based subword splitting is more useful for some languages than with others. So for some languages where there were like stems or different stems get changed based on the different suffixes, like in Hebrew, BP is simply not a great tokenization paradigm. Secondly, given that the subword vocabulary for these methods is generally trained on the same data that these languages are trained on, the way these words are segmented generally favors languages that have a lot of data already in the pre-trained data. So typically we see that for English, most English words will have one token associated with, or most English words will have one token associated with that particular word in the target language or in the vocabulary, whereas for languages with much fewer data during pre-training, each individual word might typically split into like 3 or 4 different words, and particularly more so for morphologically rich languages. And in most cases, because the splitting is simply done based on frequency, this does not restrict or does not is not in accordance with any sort of morphology or any linguistic intuition at all. So I really think overall that improving segmentation for these methods is one of the biggest factors, or the biggest ways these can be improved. And I guess one way, I mean, what I mentioned before in terms of learning these new embeddings for the target language, to some extent this helps with that, because by training a dedicated tokenizer just for that particular language, at least this makes sure that tokens in that language will get, at least within the realms of PP, properly represented. And with regard to your second, sorry, could you just repeat, remind me of your second question again?
That was about using transliteration for different scripts.
Yes, that's actually there's been a recent paper on that, which basically essentially proposed to transliterate languages with different scripts to English, or to like the Latin script, and then showed that actually just by doing that you can get quite a reasonable performance. However, I think that's a good band-aid, or like a good baseline to use. And but I think overall, if we really want to learn representations or models that can adequately represent like information and knowledge in different languages, I think we should really be able not just to map them to some intermediate or some different script, but get the most information out and model as well as we can the particular script of the target language. So while I think that's a good intermediate approach, I think ultimately we should try to do better than that.
Right. Maybe I can insert a follow-up question here. So it seems that like multilingual BERT is a fairly good first starting point, and the reason that it has been trained on multiple languages sort of captures a lot of these regularities. One thing we found when we tested this systematically is that whenever there is actually a language-specific version of BERT that has been trained on a particular language alone, in whatever way, shape, or form, it tends to outperform the multilingual BERT version for that language, even if you do like, joint training or something. So I'm wondering, so that seems to indicate that if people who know the language and who have access to better resources and sort of can dedicate time to annotations and whatnot, you can outperform this approach. So the question is, like, obviously there's a huge gap right now between different languages and sort of the number of available resources. Do you think, and you mentioned that in one slide also, the best thing is to add more data. So if you have more data, do you think a lot of these tools that you've and approaches you've shown today is sort of the way towards getting to that point where under-resourced languages can gear up in terms of resources, and that is the final frontier? Or do you think methodologically we'll get to a point where we can, no matter how large the amount of resource data is for a language, we can get to the level of English or even human performance, which seem to be the closest right now?
Yeah, I think, I mean, we also recently studied, like in a separate paper, kind of this comparison between monolingual BERT models and like this multilingual BERT across different tasks. And what we saw there is actually that kind of one of the biggest factors for like whether a monolingual BERT model is better than multilingual BERT is whether for that particular language, multilingual BERT has seen a kind of sufficient amount of pre-trained data, and whether and how similar the tokenization or like the way words in the multilingual vocabulary are segmented compared to the monolingual model. So in general, if those are like somewhat similar, and if the multilingual model has like a somewhat good segmentation of the target language as well, we've seen kind of similar performance by just applying them in the monolingual setting as well. So that's kind of one comment. I think generally, when applying these methods to language, I think when the language is already covered by these multilingual models, I think that's a good baseline already, something good to use. I'm not sure, personally, I don't think that training like kind of these monolithic pre-trained models for each language is kind of the way to go, because with each new better model that comes out, we might we have to redo the same thing for all of those different languages. So because of that, I think something that is like more scalable, more parameter efficient, such as adapters, which can be even pre-trained with like on a single GPU relatively efficiently, and like shared and downloaded more efficiently together with one multilingual model. I quite like this sort of kind of more modularity, more kind of sharing compute type approach, basically. And I mean, ultimately it's still, I think in the very end, it's still a question of like data availability. Ultimately, like we will be able to do more by exploiting data from similar languages, from like similar language families, or with like similar linguistic typology. But I think ultimately for these methods, getting really expecting to get like the same performance or the same high level performance, at least with current techniques as English, where you have billions and billions of pre-trained data tokens, is still quite unrealistic right now. But I hope that at least for like, because many of these methods, like both in terms of working on more sample efficient methods and doing more with less data, that we can get to that and actually bridge the gap to some extent, that we'll see that gap mainly on the most challenging of tasks.
Okay, thanks. Do we have other questions? I would especially encourage students to ask questions. This is a great opportunity to talk to a specialist like Sebastian. I see a raised hand here, Max. Just if you just want to, you can just unmute yourself and ask, or if you have audio trouble, you can also write.
Hi, thanks for the opportunity. I was wondering, more generally speaking, since your work focuses on getting the cross-lingual representations to align, do you think there are any useful priors that you could use during training to kind of enforce a similar structure across languages?
Yeah, that's a great question. So I think, I guess so far most of the work that we've done and that I've seen has centered mainly on priors in terms of like similar lexical information. So previously for like also in the realm of like learning cross-lingual representations, we've seen that having these like shared subwords or even shared, people have looked at like similar character engrams or kind of sharing some information in terms of like the string or lexical level. That has been useful, as well as I showed with this lexical overlap initialization. I think beyond that, there hasn't been like, yeah, I think beyond that, there's been relatively little work. I think the main, maybe other relevant thread is here that some people have used kind of typological information. So there are these databases available, such as the World Atlas of Language Structures, WALS, which essentially capture a huge number of linguistic features from many different languages. And people have used these feature vectors for conditioning or for like generating some particular parameters condition on that. So I think that's something based on this feature vector, potentially the model might be able to learn some typological similarities or get some prior on like at least a linguistic level of language similarity. But beyond that, I'm not aware of any other like relevant work. I think it would be very interesting to, like given that what I outlined, what I think is still an issue with zero transferring kind of for syntactic information or information that is kind of more dependent on like dependencies or like word order, information like that. I think it would be very interesting to encode these more directly or provide these more explicitly as priors into the model training. But I haven't seen anything directly based on that other than like beyond simply kind of using word alignment information in pre-training.
Sounds interesting. Thank you.
We have other questions?
Hello, I have a question. What are your thoughts about tasks such as its cultural bias could be impacted? For example, this task could be example of fake news detection or maybe offensive language detection. What are your opinions using cross-lingual embeddings for transfers task that is learned by this task? Yeah, this is my question.
Sure. So if I understood the question correctly, like the question was about how we can use these methods like cross-link embeddings for tasks which are kind of culturally like
yes.
capture some cultural information.
Yes, exactly.
Okay. Yeah. Okay. Great. Very interesting question. I think yeah, to the extent that like culture or like cultural knowledge is like captured in data, I think definitely like to the extent that you train these methods on unlabeled data of a particular language, I think they can definitely, I would like my intuition would be that they can able to pick up on some like culturally relevant information. Of course, I think it really depends on what you kind of how you find that, like how you yeah, for also related to what particular tasks those are interested in, like those are relevant for. I've seen, yeah, for instance, for tasks that require some like common sense reasoning with a cultural component. I think something like that might be a lot harder to do compared to, yeah, even fake news detection. I think is still like is one of the most challenging applications at the moment. So I think while these methods could be used as a good baseline, I don't think there's anything. I think you need to think like a lot more explicitly about like what maybe training them on different data or making them more sensitive to that information, because as it is now, I think that information, if it's captured to some extent, is probably very, very latent, or yeah, only minimal in those models.
Thank you so much.
I can ask a question if that's okay. First of all, thanks a lot, Sebastian. That talk was really rich. I was just wondering, going back to the transliteration, which I think is a simpler task than translation, because basically you have the same language that's written in different scripts. On that basis, wouldn't it be quite smart to use something that's less computationally expensive, like the previous cross-lingual word embeddings, word2vec, fast text, because we really don't care about the context. We are just converting one word to another word to transliterate the text. So I mean, all the literature and all the state of the art is about BERT and multilingual BERT, but in such a case, would you reckon go back to the older methods and see if it's better, or what do you think? What's your input on this? Yeah.
Yeah, I mean, I think ultimately it depends, like what your application is, what your downstream setting is, and what you particularly care about. So yeah, you mentioned that these methods, like kind of the new methods, they are more powerful, but also a lot more parameter expensive, a lot more inefficient, have a lot higher latency compared to previous methods. So if you're in a setting where those particular cases are important, I think either going back to previous methods, so simply, I mean, yeah, so I think the latency, like efficiency of your setting is important, as well as the complexity of your task. So for something, if it's simply like a document classification task, we try to assign topics or news categories, something like that can be simply using like word level translations or cross-lingual word representations. But if it's something that requires a bit more reasoning or question answering or so, you're generally better off using these like more recent methods, and maybe then if those are too large for you, maybe distilling them to a smaller version to get more faster and more parameter efficient methods. Yeah. So I think, yeah, those two kind of points, difficulty of the setting and just the general latency that you need, I think is most important.
Okay, thank you so much. I was also hoping if we can get the slides that you presented today. You are going to share them somewhere.
Sure, yeah, I can share them later.
Yeah, thank you.
Yeah, we also have the recording of the talk, and we might be able to make that available in some way, shape, or form.
Yes, we should be able to publish the video. All the participants have filled a form giving the consent to the publication of the video, so we should be in good shape to share it.
So I'm wondering, more general, and this already came a little bit through, is this, are these approaches applicable more general to a wider range? There's been a lot of more interest lately in bias and, sort of all kinds of sources of this bias, unbalanced data, sort of models that try to, find like an objective function and exaggerate any biases found, annotation biases, but also, cultural presets, norms, expectations, and other things that sort of influence this. And can we zoom out and say that a lot of these approaches might also be applicable in addressing some of the other, let's say, individual presets and biases that we haven't covered as a field yet? So be that differences in demographics, differences in cultural norms, like what is polite or impolite in different languages to say, what can or can you not say when somebody asks you, do you think this is sort of the germination point to tackling a lot of these other problems as well, or is this just one step along the way, and there are horizons beyond what we see right now?
I mean, I think this like these generally not just the recent methods, but also cross-lingual like representation methods, I think are useful methodology, useful toolbox to allow us to study using some of these cross-lingual phenomena. I think, I mean, yeah, one limitation I think at the moment is just that in practice I wouldn't know where to start or where we don't have, I think, very good high quality labeled data or labeled data sets really to try to like evaluate or even address what are all the possible kinds of biases that we want to look for, or particularly I guess as a field we're only just starting doing that for English in some more systematic degree, and I think there's been some promising efforts in terms of addressing bias in terms of translation, but I think we're only just at a starting point for really looking at this in a cross-linguistic comprehensive setting. Yeah, but I think that overall I think that for the entire field is a really important direction, and I'd really like to see more work in this area.
Thanks. And there's another question by Johan.
Yes, I was just thinking, because I'm working on something related to this right now. This adapter-based approach for adapting to the masked language model pre-training of another language. I mean, could this also be used for adapting to a different domain of the same language, maybe? Because I mean, you're always stuck with whatever was used for the original language model training, right? So then you come up with a completely, like, it's the same language, but it might be a huge corpus you happen to have on a different domain. So I think that should work actually with that adapter-based approach to maybe improve your language model, right?
Yes, yeah, I completely I completely agree. I think these adapters in general, I mean, even though we use them in this setting for adapting to languages and tasks, they can generally be adapted, used to adapt or learn representations for any setting, any often low resource setting that you particularly care about, whether that is learning domain-specific representations for particular user groups, for particular demographics. I think all of these are potentially really valid, and I think useful settings for these methods could be useful for. And then I guess in practice it's just a matter, I think, one still slightly open question in terms of how you want to combine them, whether stacking them really is the best option, whether it's better ways to do that. And if you're already generally kind of, if people are interested or curious, there's this thing that I briefly highlighted, this adapter hub, because in another paper some other people actually trained domain-specific adapters for all representations of the the kind of Stack Overflow and other related question answering forums online, and I think those adapters are also available for download and for training as well.
That's great. That paper, if you maybe can share a reference, because I mean, just a follow-up question. I understand this correctly, that this kind of adapting the masked language model is much easier to achieve with respect to the resources required, right? I mean, that should happen much faster than actual masked language model pre-training, right? So that's something I could do. That's what I like about it.
Exactly. Yeah. So this, so pre-training, I think, or training a huge model, particularly these huge multilingual models. I think for that you really need huge amounts of compute. But a really nice thing about these adapters is that like in our cases, we always train them effectively like on Wikipedia or on data of a particular task. And yeah, in generally using like one or two GPUs in, I think in most like one day or 2 days, I think, for the ones with the largest Wikipedias. So in practice, because you only train such few parameters, it's really something that is quite scalable with limited compute as well.
Great, thanks.
Right. I think that brings us to the end of the allotted time, trying to be mindful of people's schedules. Thank you again so much, Sebastian. And you know, this is not a real in-person talk, but I'd invite you to unmute yourself if your audio and bandwidth allows that, and give Sebastian a round of applause for this great presentation. So thanks very much. All right. Thank you, everybody. Thanks for the great questions. Thanks for the wonderful talk. There are some one-on-one meetings taking place. I also wanted to remind everybody that we have our Iperitivo, the online session where we have a refreshment and we chat sort of more in a more informal setting. That's going on later, 6 p.m. Milan time. Don't know what time that translates to where you are. But yeah, also this is open to everybody. Tom, do you want to say a few things about the modality?
Yeah. Yes. Just a moment. Okay, I am not unmuted. If you feel like to take part in our online aperitivo, I just copy the link on the chat. So just fill it's a sheet. Just fill it with your email, and I will send you the link for the aperitivo. It will take place at 6 o'clock Italian time, which means 5 o'clock UK, and make your own calculation for yourself. I just share the link. Okay. So with this link, you should be able to access the sheet. If you want to just leave your email, and I will send you the link.
Great. Thanks, Tom. All right. Thank you very much. Oh, we make the recordings, if we get the permission, we make the recordings available on the DMI website. So dmi.unibocconi.it. We also have like some of the previous talks recordings there. All right. Thank you again, Sebastian, and everybody. Have a great rest of the afternoon, and hopefully see you all soon. Ciao, ciao.
Thank you.
Bye. Ciao, ciao.